Hello, I'm here to talk to you a little bit about sound and sound waves. So sound is caused by the collision of molecules in the air or in certain materials like solids, for example. When I speak, it basically causes a cascade of molecules to bounce into each other, to bounce into other ones, and etc., etc. So it's not the air molecules that are actually moving through the air from my mouth to your ear. It's the energy that is caused by a collision of many, many different air molecules. So if you look at this picture here, I've got compressions drawn here and rarefactions. But imagine this, if you had one different air molecule, it might bounce back and forth and back and forth and back and forth, but it's not going to go very far. So again, like all longitudinal waves, the motion of the molecules is in the direction of the motion of the actual wave itself. They both are going to the right, for example. I'm going to assume this wave is to the right, except the actual molecules go to the right and to the left, and they don't move very far. They stay more or less in the same place. As I said, it's a longitudinal wave, aka a compression wave. And I've drawn compressions and I've drawn rarefactions. You could measure the wavelength between them, for example. Air is a very common medium for sound, but you can travel through other media as well. But you do need a medium of some sort. So you cannot have sound in space. So no sound in space. Just doesn't work because in space, space is a vacuum. And a vacuum has no air or no medium for those molecules to collide with each other. We'll often talk about the frequency of a wave as its pitch. So high frequency would be a high note like a ah. Low frequency would be a low note like a ah. And you can have a variety of different frequencies. Obviously the wavelength of a wave is related to the pitch. They have an inverse relationship. As one goes up, the other goes down if the speed of the wave remains the same. But strictly speaking, the pitch of a wave is dependent on the frequency. Amplitude determines the volume, and amplitude also determines how much energy is in the sound wave. So the more amplitude, the louder the wave, the more energy it has. And the higher amplitude, the softer the wave, the less volume, and the less amplitude, and the less energy. There's other wave properties we've introduced, like the Doppler effect, and interference, and diffraction, and resonance, and they're all perfectly valid for sound waves. The one thing that we've seen that is not is polarization. That only affects light. So you can have the Doppler effect of sound wave getting like a car driving toward you, or you driving towards a car that's honking its horn, and when the car is coming towards you, the pitch gets higher, and when the car is driving away from you, the pitch of the horn gets lower, which is why when cars go toward you, you often hear like a loud vroom. So the actual pitch will get less as it's going away from you. The volume also tends to get less as it's further away from you too. Let's see. I think that about does it for sound waves. I know a lot of this is a little bit redundant. One other thing to just keep in mind is that as it's a compression wave, and compression waves depend on the material they're moving through, denser material sends the wave through faster. So the speed is about, I don't know, 340 meters per second in air, but that depends on the temperature and the pressure. So if you look on the reference table, it will actually tell you the speed of light at standard temperature and pressure, which is a little bit less than 340, but STP is a little colder than most rooms that we talk about. But that depends on the material, so it's faster in solids and liquids, for example. Because those materials are denser, and it allows much easier and faster collisions between molecules, so the wave travels faster. I think that does it, as a sound introduction. We'll see more of this in class. We'll do some cool labs with sound as well. Thank you very much for watching.